Tá a funcionar o som? Ok. Pom, pom, pom.
Okay, I think we can start.
Okay. Okay, very good. So, thanks a lot. So my goal today is to just review some known formulae for how the conformal data, the energies and the structure constants of some particular class of operators in n equals 4 super Young mills looks like. So the main motivation for just doing this small review, because I know that some people are trying to think of what could be a worldsheet formulation of ADS5 at small radius, how could we try to develop some approximations to try to derive weak coupling, n equals 4 weak coupling results. So I think it's useful to know what form they take, how do they look like, so that if we want to come up with some alternative derivation, we know what we are aiming at. So I will review basically two formalisms that showed up in the last few years that study an object that we don't know yet how to study efficiently with integrability at any value of the coupling, but we are getting there, which are the structure constants, the interactions between the operators. So in any CFT, the CFT data is the spectrum, and the spectrum is super well understood, and I'm not going to spend too much time on it, and the structure constants. And the structure constants, we have some hints on how to formulate them, but we don't know exactly what's the best formulation yet. And in analogy with the general quantum system, the spectrum is like the energy levels, whereas the structure constants require knowing the wave functions of the states, because we are going to really contract the states with each other. So it's a bit like looking either at the energy levels or looking at the details of the wave function. And of course, looking at the details of the state is more complicated, but it can also be interesting. If we are after some kind of string bit model on the worldsheet where we see the bits of the string, maybe seeing these wave functions and seeing these structure constants and seeing what form they take is perhaps even more instructive than looking at the spectrum of energies. So that's one motivation for asking how they look like. So the simplest thing we could consider, the simplest set of operators I'm going to consider are operators in what we usually call the SL2 sector of the theory. The SL2 sector. So I can think that I'm studying, for example, operators that are like this. So I will have operators made out of one null vector phi y1 dot phi, and I can have many such combinations of scalars y1 dot phi. And I'm leaving space, of course, because I'm going to make this operator more interesting. That could be one of them. And then I could study 2-point functions or 3-point functions, and the other one would be simpler. The other one would be the same thing, but with another null vector to some power L2. And the third one, if we are going to study 3-point functions, would be also very simple. It would be trace of y3 dot phi to the power L3. So these three guys, these two guys here in the bottom, they are BPS operators. We are always going to study the planar limit. And these guys, there's not much more to say. The dimension of these operators is just equal to the dimension of the operators. There's no quantum correction. And if I were to study correlation functions of three of these guys, it would be whatever you get at 3 level, and it doesn't receive quantum corrections. So you would just do the planar weak contractions, get some result, and that's it. So what's interesting is that I'm not going to just consider this guy to be the BPS guy, but we are going to consider this SL2 sector, which means that I sprinkle this state with some derivatives in one of the light cone directions, and I put a bunch of derivatives of this state. And I can put these derivatives at some position x1, another derivative at position x2, and there can be in total s derivatives, so all the way up to position xs. And not all fields have derivatives, of course. I mean, there are many y's, and some y's are acted by a derivative. And this state would be a state that has spin s, and dimension would be L, which would be the number of scalars. Let me call it L1, like this L2 and L3, plus the spin of the operator, plus the quantum part of the interesting quantum part, the anomalous dimension part. Okay. Now, before I give more details, because this, strictly speaking, is not exactly the operator, I cannot just put derivatives where I want. I need to consider linear combinations of such operators. But let's just make one comment first, that this operator here, where would it live? It would have spin. So because it has spin, this would be dual to a string that would live in some ADS3. So it's rotating. So the more angular momenta, the bigger it is in ADS3. And then it uses one U1. You can think that is y1 dot phi. You can call it z. So it lives in some, it would live in some S1 inside ADS5 times S5. But then the full thing, when I include the other ADS operators, would be living in some ADS3 times some bigger S. I think S3 is enough probably to put everything. Okay?
Sorry, what did you mean by the x1, x2 here? They're not the position of the y dot phi?
No, the x1 and x2 are, okay, so this x1 and x2, they are numbers between 1 and L1, integer numbers. They tell you where do I put the derivative in this state. Okay, so they are positions on the worldsheet, not in target space. This operator is inserted at some location, of course. Let's put this guy at 0, this guy at 1, this guy at infinity. Okay, those locations are not important. Okay, so in the same way that we can put the points at 0, 1, infinity, I can rotate this y1, y2, y3 so that I don't use the full S5. I can just use some S3. And this would be some complicated string configuration a priori that would live in this subspace of ADS5 times S5. Okay, so this is like a string bit, right? I have a bunch of phi's all the way from 1 to L. And then I have some derivatives that are somewhere here. For example, this could be a state with 4 derivatives. Okay, so the derivative would be here at some position 2, here at some position 6, 7, and 9. And this would be an example with L equals 10. Okay, so there will be some derivatives there. And the precise operator is a linear combination. So I have a wave function for x1 up to xs. These derivatives, these small excitations, are all indistinguishable. So when I sum over all the x's that are ordered. I don't lose anything by saying this. Right? I sum over all identical particles. And then I have some wave function that some linear combination of this state. And this wave function depends on some parameters u1 up to us that I'm now going to specify. And the idea is that this wave function is fixed such that this state has definite anomalous dimension. Okay. And that fixes this wave function.
Are the xi's distinct?
The xi's are not distinct. Good point, yeah. So the xi's are smaller or equal, you're right. That's a good point. So these particles are not hardcore. In particular, I could have, say, two derivatives here. Okay, so they are small or equal. They are moving around, and they can be on top of each other, and so on.
Divide by some symmetry factor?
Sorry?
It's cyclically symmetric, so you should divide by some.
They are cyclically symmetric. That's right. Yeah. So that means that this wave function should be the same if I shift all x's by 1. There should be some total zero momentum condition that we have to impose here. Okay, good. So let me tell you very quickly what is this psi that depends on all the u's. But the punchline is that the key thing are really these u's, that parameterizing a state is given by parameterizing these u's. And once we have these u's, we can compute the energy of the state that depends on u, or we can compute this structure constant c that will depend on the u's. Okay, so I should tell you what are these u's and how do they describe this string bit, this string. I call it string, of course, because as Nathan just said, it's like a trace, so it's like a discretized string. So how do the u's parameterize the wave function on this discretized string? And then once I have the u's, what do I do to get this CFT data, the 2 and the 3-point functions? Okay, any question here? Okay. So let me tell you what this wave function looks like. So let me just write it for an example for s equals to 2, and then I will write it down. I will write it in a formula, then I will write it graphically, and then the generalization will become clear. And the idea is the following, is that this wave function looks like this. Let me write the result, and then I'll tell you what's the interpretation. It looks like this. So there is u1 plus I over 2 over u1 minus I over 2 to the power x1. Then there is the same thing with u2 plus I over 2 u2 minus I over 2 to the power x2. And then there is a term which is u1 minus u2 plus I over u1 minus u2 minus I, and the same two exponentials, but with x2 and x1 swapped. Okay. And so what is the interpretation of this wave function? Is that I have two locations, I have two derivatives that are moving on the C, and one derivative is raised to the power x1, one derivative to the power x2. So this combination here, I can think of it as the momentum of one of the derivatives. So this would be the momentum of one of the derivatives. So I think I have my derivatives, and one of them moves with some momentum p1, the other one moves with some momentum p2. And so I think that there is some momentum p1, some momentum p2. So there is just some simple map that relates p and u. So u is like momentum. And then this is like an incoming state where I have two momentum. This is like some incoming state. Here the momentum gets swapped, so this is like some outgoing state. And so this is what I would call the worldsheet S matrix S that depends on P1 and P2, that tells me what is the weight of the out state when the in state is normalized to 1. So it's really the coefficient between the in state and the out state. So that's the interpretation of this wave function that we write graphically as saying I have some incoming state plus some state where the particles get swapped, and the price to pay is an S matrix. Once you write this, then the idea is that the generalization to more particles instead of getting 2 terms, I would get now n factorial terms. Let me just write 1, would be just an incoming wave, and then I could scatter particle 1 and 2, and I would write something like this, or particle 1 could scatter with 2 and 3, and I would pay 2 S matrices, and you get 3 more terms, and this would be a wave function with 6 terms. And this wave function with 6 terms was the wave function that Bethe proposed. That's what it's called the Bethe ansatz. And that's not obvious. When you have 2 particles in 1 dimension, this form is more or less obvious, because if you have conservation of energy and momenta, the particles can only bounce. But for 3 particles, it's not obvious. If I tell you I have some incoming states, the outgoing state could be a mess, a priori. Doesn't need to be just reshuffling of the particles, but here it is. And it is because this worldsheet is integrable. Okay. So finally, let's just remember that once I have this wave function, then the energy of my state is a simple sum of the 't Hooft coupling to leading order in perturbation theory divided by u squared plus 1/4. And so I think of this as the energy of my excitations with momentum Pj. So if you put 2 particles, you sum 2 such terms. Okay? And moreover, and lastly, but very importantly, of course, this spectrum is not continuous because these U's are quantized. And they are quantized by imposing, of course, that my wave function, that's a trace, like Nathan was saying, it's periodic. So if I impose that my wave function x1, x2 is equal to my wave function when I shift, say, x1 by L, all right, so I wrote like this because I want to preserve that they are ordered. So when I shift x1, I write it like this. So if you impose this equation, you plug it here, you get the following equation. I'll write it already for n particles. You get the equation that ui uj plus I over 2 over uj minus I over 2 to the L times product of k not equal to j uj minus uk plus I over the same thing with minus I is equal to 1. That we represent as saying that I take a particle. This was e to the ip, so there is a phase when the particle goes around. That's just the momentum of the particle. But then it scatters. We identify this with the S matrix, so it scatters with everyone else. And so this is just a statement that the total phase as the particle goes around is equal to 1. And this one, to parameterize the various solutions of this equation, we often take the log of this equation and impose that this is equal to e to the 2 pi I times some integer nj. Okay, so before we continue, let me just stress that this is very much like usual strings. So let me just maybe in red emphasize the analogy with usual bosonic strings. For example, what would be the analogy between this and usual bosonic strings? Normally in bosonic strings, we could have some wave function that would depend on the locations. Normally we would call them sigmas instead of x. There would be some continuous variable sigma on the worldsheet. Then on the string we have mode numbers, n. And these mode numbers of the string in flat space, these n's would be the mode numbers of the string. But the string is free, so there's no S matrix. So basically n's of the string in flat space are up to a constant directly the momentum of the excitations. The momenta are quantized because the modes are free. The S matrix in flat space would be 1, right? I just have a bunch of bosons. There's no S matrix between them. They don't scatter. I just I excite a bunch of modes on the string and they just move and they don't scatter with each other. And so these Bethe equations, this statement is 1, is just a statement that the momenta are quantized. And then the energy would be in flat space just proportional to the momentum. And this would give us the mass square for the string in flat space. Okay, so these ingredients are very much the same as the ingredients for the string, but a little bit more complicated. Namely, there is a non-trivial S matrix, so the string is not free anymore. The excitations on the string, they scatter. The momentum and the energy are not trivially related to the mode numbers. In fact, I parameterize a given set of mode numbers, and I could say that the momenta are some function, some complicated function of the mode numbers. So, but in general, it's not as trivial as in flat space. And in particular, there's no decoupling between left and right movers. There's no such thing as left and right movers as I have in usual string theory, where I have some left movers and some right movers. And here I could say that some n's can be positive, some n's can be negative. They would be the analog of the left and right movers, but they talk to each other. There's no particular thing that says that they are decoupled, because the worldsheet is more non-trivial and it doesn't factorize as just allomorphic and anti-allomorphic. Okay, but otherwise it's really the analogy, so this would really be how I would think of some quantum small string.
Of course, you're just talking about the one of approximation.
That's right, that's right. This is going to be, I'm going to describe n infinity and the smallest coupling today. Yeah.
So what is L in flat case?
L in flat case could depend, would be, for example, depends on the gauge. So if you fix, for example, in flat space, let me continue with red. For example, suppose I fix global time to be equal to worldsheet time. Then what's the energy of my string? The energy would be some integral over sigma, right? Of derivative with respect to tau of t. That's just 1, right? So in that static gauge, for example, the length of my string would be the energy, for example. If you are in some light cone gauge, you would associate different lengths. The natural lengths of your string could differ. Right? So that's a bit gauge dependent. And the way I think that it's gauge dependent in this picture is that here, for example, I could decide to put some factors. I could put some factors here that it could be ambiguous whether I associate them to momentum or to S matrix. So this L is actually not totally unambiguous. I can shift it a little bit and put part of it in the S matrix. Okay, ignore that comment if it was a bit unclear, which probably it was. But anyway, so, right. Okay, so the claim is, again, let's stress. So there are these important equations that quantize the use. So given you take these equations, there are S of them, right? So there is, for each particle, I have one such equations. So I take these equations, I solve these equations, and I get a set U1 up to US. And then I take this set, and I plug it here, and I get the energy of my state. Okay? And that's it. So that's an example of how do I get the spectrum at weak coupling. Again, in flat space, it's even simpler. You give me some set of mode numbers, and I write down the mass immediately, right? There's no equations to solve because there it's trivial. So here, you give me a set of mode numbers. You still need to do some work to find the moment of the particles. But otherwise, it's conceptually the same. Okay. So let me, so now you see, I have this wave function. It's written by this type of bit ansatz, where the U's obey these equations. So I could compute the structure constant as well. The structure constant is just weak contractions, right? So you just do weak contractions, you put a point at 0, one at 1, one at infinity, you do these combinatorics, and you get that this structure constant is going to be some function of the U's. Just obtained by plugging that wave function here and doing these weak contractions. So let me write, I want to write what this is. So it's given by some normalization. And this normalization, of course, I can normalize the 2-point function to be 1 then it makes sense to talk about the 3-point function. So that normalization, for example, includes the norm of the state. But the interesting part, the genuine interaction part, takes the following form. It's a sum. So this is, again, just the result of doing combinatorics. You just take this wave function, you know, and you connect with propagators here. And this part is boring, so nothing happens here. And the interesting part is what happens in these propagators up here. So you just do this combinatorics. And the result is the following, it turns out. It's a sum over, you take your roots and you split them into two groups, alpha and alpha bar being the complement of alpha. So you see that there are 2 to the s terms, right? So it can be empty, full, one element, almost everyone, etc. So you sum over this. And then the result you get is -1 to the number of elements in alpha bar. And then there is a product over the elements in alpha bar of uj plus I over 2 over uj minus I over 2 to the power L, and then a product over j belonging to alpha and k belonging to alpha bar of 1 plus, or let me write differently, of uj minus uk plus I over uj minus uk. Just this. Okay? So that's the result of doing some combinatorics. And this L is this L here. So that L is L1 plus L2 minus L3 over 2. Is what we call the bridge length. Okay. Okay, good. So that's the formula at 3 level, and then at the leading order, and as she said, and then there are corrections of order lambda. This would be from a 2-loop computation, whereas this stuff was the result of a 1-loop computation, even though it comes with lambda to 0, right? So we had to diagonalize the Hamiltonian at 1 loop. We got some wave function. We compute the structure constant. We get this result. If we corrected the wave function, it would be order lambda, etc. All the way to strong coupling. Okay. So that's the result of some combinatorics. That this was the result now the idea is to try to interpret this result, to try to look at this result, and in the same way as we looked at the final formula for the energy and we had a clean interpretation, it was the sum of the energies of various particles. The question is, what is this formula trying to tell us? What is a formula like this, which is just the result of weak contractions, trying to tell us for what's going on in this picture of 3-point functions?
Alpha and alpha bar refer to the 2 sets of contractions with L1 and L2?
No. No. In fact, for example, you can say that if I put this, no. For example, if I put operator at 0 and infinity, this depends on the conformal frame. But if I put operators at 0 and infinity, derivatives here are suppressed. Because you see, this propagator is 0 minus infinity square. If you take derivatives, it's 1 over infinity to the cube, 1 over. So when I put this in this conformal frame, for example, all derivatives, they want to go here, in this particular conformal frame. Of course, the result is independent of the conformal frame. I can put infinity here. Now all derivatives want to go there. So it's not. It is just the result of taking this wave function and doing the weak contractions between these states. And we can open some book on scalar product of quantum spin chains, and we get this result. Okay? Yeah, I'm sure it's correct, yeah. It should be, right? So, okay, so I can comment on that. So how do I see that it is symmetric? So this formula is symmetric under small l goes to capital L minus L. That is doing the operation you said. This operation is swapping L2 and L3. Okay? And the idea is that if I put here capital L minus small l, I can show that using bit equations, the equations in the box, that this equation is invariant. Okay, so this requires using Bit and Zatz equation. That's actually a hint. This symmetry is actually a hint. So the question is, what's the interpretation of this formula? Okay. So the idea, so you see that here, actually it took us a while to come up with a guess for what this formula was trying to tell us, because it's written in a way that's a little bit misleading. It looks like we have two sets, alpha and alpha bar. There is some propagation stuff, and then there is some interaction between alpha and alpha bar. Okay, it looks like alpha and alpha bar, they are interacting with each other, the group alpha and alpha bar. And that's not the correct way of thinking about this expression. So let's rewrite this expression in the case, again, for s equals 2, because it was quite instructive also there for the energy. So let me write what this is. So then this formula takes the following form. It takes the form. So let me explicitly do the sum. So there is one term which is all elements are in alpha bar. So there is no product here. And here there's no element in alpha. And this is 1. So the first term is just 1. Then there is the term where one element is in alpha. There is a -1. Then there is e to the I p1. Or let me write first this one. p2 times L times, let me denote this function here, fjk times f12. Then there is a term which is plus e to the I p1 times L, also with a -1, times f21 plus e to the I p1 plus I p2 plus p2 times L. And now let me further factor out f12 here in front. And if I factor out f12 in front, then here I define hij to be 1 over fij. And now I factor out f, so here I have this. Here I have nothing. Here I have h12. And here I factored out f, so I have h12. And then I have the ratio f to 1 over f12. Is this correct? Or did I do some algebra mistake? So, sorry? It's incorrect, right? Sorry? So it should be...
You're either having h12 or the 1 over f12, but not both.
Okay, so I divide everything by f12. So I wanted to write...
h12 is already 1 over f12.
yeah. That's good. Perfect. Okay. And now, that's great. And now you see that, okay, this was the outcome of just doing some perturbative computation, but you realize something nice, that the ratio of these two functions here, when I take the ratio of these two guys, this is actually exactly the S matrix between excitations 1 and 2. Right? This f over f, this stuff cancels, and the ratio of this guy was exactly what we had identified with the S matrix. And now a picture emerges. It looks like this is telling us the following. So let's now interpret this formula, which was this result. It looks like there is a term, h12. Then there is here basically nothing. Let me write here 1 times 1. Then there is an S matrix times nothing. Let me write this as 1 times 1. And then there is again h12. And so the picture that starts to emerge is the following. Is that what we are doing is the following. We have our state that had two derivatives. And we were computing this pair of pants. And we decided to cut the pair of pants into two hexagons. So we decided to take this diagram and think of it as the triangle inside and the triangle outside. And when you cut this, what happened is that you had two excitations here. And the excitations could end up in the front. And if they end up in the front, then if this is particle 1 and this is particle 2, I have the hexagon expectation value. There is some kind of hexagon in the front, expectation value with particles 1 and 2. And that's how I interpret this function of rapidities 1 and 2. But when I cut this hexagon, what could also happen is that when I cut, particle 1 was here, but particle 2 had traveled to the other side. So now particle 2 is there. And now that particle 2 is on the other side, when I cut, I get the hexagon with a single particle in the front times an hexagon with a single particle in the back. And that I interpret as this 1 times this 1. And what phase do I pick? If a particle propagates across this bridge length of bridge L, I pick e to the IPL. So that makes sense. It's the particle 2 that was here, and that propagated to the back. Let's look at the next term. The next term is when particle 1 propagates. But now particle 1 was ordered. Particle 1 was coming before particle 2. So particle 1 to propagate to the other side, it should pass by particle 2. So it should scatter with particle 2. So the particle 1 here could end up on the other side, but then it propagates, but it also scatters with particle 2. And then once it's finished, once it goes there, it's one particle in the front, one particle in the back, 1 times 1. Or finally, last one, both particles could be in the back. And that means we just move this as a whole to the other side. So there's no need to scatter. You just move the full. You just move both particles. And then you don't pick any S matrix. And now they are on the back. And you get another H factor.
So from the middle two terms, what replaces the matrix element of H hat?
1. It's just that now it would be 0, H with single particle. That's a normalization. That's normalized to 1. And so once you write it in this form, whereas before it looked like the alpha and alpha bar are interacting, now it's the extreme opposite. Is that things, they interact just because they need to pass to the back. So the interaction is all factorized. It's just a bunch of S matrices, like in this case. But once they are in the back and in the front, we just get hexagons that just depend on alpha, or hexagons that just depend on alpha bar.
Have you tried to reorganize this sum to put these features so that these features are evident?
Right, so that's what you can do. You can write this sum as a sum of some weight factor that takes into account the passage of whatever particles need to pass. And then once you put this weight factor that will depend on L, then the rest would be some hexagon that will depend on alpha bar times some hexagon that will depend on alpha. Of course, it's not the way it comes about. It comes about like this. But you are right, it can absolutely be written like this. And once it's written like this, but you needed to do this simple example, otherwise it would be hard to do. Now that you wrote it like this, you see that there is this factor that represents the propagation of the fact that particles were in this bit ansatz. And so for them to propagate, you need to pick some weights. And then there is the alpha and the alpha bar hexagons for the particles that ended up on the front and on the back. And that answers Nathan's question about this being L2 minus L3 or L3 minus L2. That was because we decided to think of particles as going in this direction. But of course, particles will go in the opposite direction. And that's, but the full state is periodic because that's what bit ansatz gives us. So going everything is nothing. So going half or going the other half is the same. Okay, so and indeed I could write this formula with capital L or with L minus L, and there would be a symmetry between the two. Yes?
In the third term, why can particle 1 just go to the other side without crossing particle 2?
It can, but then it would not pay this factor. Then it would pay the factor. What Rodrigo is saying, why don't I, if 1 is not well ordered, why don't I write e to the minus IP1 times capital L minus L, right? I can, but then I can use bit equations to get rid of e to the IP1L using the S matrix, and I end up putting the S matrix, right? So this minus minus is what is there, and the e to the minus IP1L is by bit equations exactly the S matrix. So it doesn't matter. I can go in one direction or the other. Okay? So I either put like this and no S matrix, or I put like this with an S matrix and it's equivalent. And so this leads to this proposal that the key object that enters these 3-point functions is this hexagon object. And so schematically, we write, and it's a bit schematic, that okay, let me write it very schematically, that this hexagon would be gluing of 2 hexagons. So I'll put some funny symbol, and the funny symbol means the formula we wrote before. Okay? And in pictures, it's really this, that the pair of pens is 2 hexagons. In fact, if you go in Wikipedia to ask what is a pair of pens, it's literally on Wikipedia. It says in mathematics, a pair of pens is 2 hexagons glued at every other sim. So, yeah. So a pair of pens, mathematicians know you can get them by gluing 2 hexagons.
Is there no extra data to keep track of all the dotted lines?
There is. Okay, so that there is. So indeed, what happens is that when you glue back, you need to insert everything that can be flowing here. And so you need to insert some resolutions of identity at these 3 lines. And so this gluing, at leading order in perturbation theory, it's just about cutting because nothing is going on there. But later, you need to add and to sum over states that could be flowing between the 2 hexagons. So in general, this gluing represents the sums that I just described over alpha and alpha bar, but also integrals over virtual states that show up at the dashed lines. But the point is that we know how to write down this expression. We know how to write down this infinite series. We know how to write at least a formal expression that works to all loop orders.
First of all, in general, what is this hexagon operator? What space does it act on?
So this hexagon operator, with some operator on the world sheet, that I can think of it as a branch point twist field operator. So you see that what it does is, if I am here, this world sheet is an hexagon. So it's an operator like those that people use to compute entanglement entropy, but typically you put an integer number of copies. Here now you have 6 asymptotic copies. So it's like a branch point twist field operator where n, instead of being 1 or 2, it's 3/2. So it's an operator that changes 2 pi into 3 pi. Right? So it implements z, it goes to z to the 3/2 or something like that.
I just want to know, is it like a multilinear function on the 6 copies of some?
Yes. It's
what is the space? So this is something with the boundary, right? What is that space?
Yeah, if you are asking what is that space from the world sheet, because it's a world sheet quantity, right? I'm drawing a world sheet. And then I'm saying this is something on the world sheet. But why do I use these words? Because in the beginning I said this is like a world sheet, but I don't have, strictly speaking, a world sheet. That's what you guys or Nathan and others are trying to write down. So I have pictures, but this should be an object on the world sheet. And then, as you say, I just put stuff on this line, but strictly speaking, there are 6 lines. So this hexagon, I should think of it as indeed, I don't know, I can put a vacuum here. And then it takes value on physical state 1, meter state 1, which is the first dashed line, physical state 2, meter state 2, physical state 3, meter state 3. So it's a 6, it is 6 states instead of 3.
Sorry, just to understand, the physical space is in what Hilbert space? So like, I think I understand Hilbert space of the magnus on the circle, but when you put the boundary, like what do you do?
Yeah, now you cut. Cutting is a bit like decompactifying. Now you lose the idea, you lose the knowledge that they were quantized. So I like to think of it as this, even though you cut this segment, it's effectively infinite dimensional because I lost the quantization of my particles. I need to somehow go off shell. So these particles here, now I think of them that in each of these guys, I put a bunch of u's. Here I can put a bunch of u's, and here I can put a bunch of u's. But also on this dashed line, I can put a bunch of, let me call them V's, a bunch of V's, and a bunch of V's. And what exactly, how do I think of this dashed line is complicated. I don't know exactly what are the boundary conditions I should put on the worldsheet, how should I define it. I'm just telling you that this formula tells me such object exists. How to define it on the worldsheet, what is the worldsheet definition of this hexagon. I think we have some ideas that strong coupling, there are some limits where these excitations on the worldsheet become free, because as I said, the S matrix becomes 1. And for example, it also becomes 1 in this BMN limit, for example, when I have very big operators. And then we can identify the hexagon exactly as branch point twist field operators with a conical excess pi. But beyond leading order at strong coupling, we don't know what these operators are.
Can you say briefly, when you generalize this to all loop, what recipe changes in these formulas?
Okay, so there are two things that happen when we go to all loops. So when we go to all loops, there are many quantum effects that I can put here, right? I start going to loops, and I have many interactions going on at loops. Plus, there are loops that wrap all around and that know about the size of these operators. So you see that basically this red stuff starts at order g squared, the coupling, related to the power of these bridges. So it's roughly g squared to the bridge size, because you need to propagate g's. It's a bit more because things are delayed by supersymmetry, so it's roughly 1 plus the bridge length. So the first thing we can do is take this bridge length, both of them, to be big. Then you still have lots of loop corrections, but you don't have these so-called wrapping corrections. Okay, so that's the first simplification you can do, is there are loops, but there is no wrapping. And that's the first thing you can do. The second thing is you have both. Okay, so let me tell you first when you don't have wrapping but you have loops. When you have loops, what happens is the following, is that in the spectrum, you have to change these functions. You have to change it into some epsilon that depends on lambda, that we know exactly what it is, this Joukowsky. This relation between P and U becomes some function P that depends on lambda. And this S matrix becomes some S matrix that depends on lambda. And then this H that was 1 over F, this function here becomes some 1 over H that depends on lambda as well. And now in the same way that Bizert and others guessed the null loop expressions for the S matrix, we guessed a null loop expression for this H. And then nothing changes. You just have this now depends on lambda, because it's the same factor there. This depends on lambda, like I said, and then this formula is just true to all loops. But if the operators are big enough. So if these bridge lengths are like 4, this would work like to 7 loops or something like that. This is a simpler factor. It would change, but it's also known.
So n includes all the y dependence, right?
No, the y dependence is boring. I did not even write. The y dependence sits in front of the correlator, and it's the same as in the BPS case.
It doesn't change for loops.
No, it doesn't change with loops. In particular, notice that this is really the interesting part of the correlator. For example, this is the part that depends on the geometry of the correlator, on this L. This normalization is just about a 2-point function. It's irrelevant. So if I make ratios, for example, of 3-point functions with different L's, only this part matters. Okay, so that's known exactly. Otherwise, you see, what would be the first correction to this picture? It's the picture where I have my particles here, for example, plus, instead of putting the identity, I put one V here, right? One virtual particle here in this gluing line, for example. That means that you go to this formula and you say there is an extra V here and a minus V here, because you put the particle and you glue it here, and you get a single integral dV. So that would be the form of the first correction. And more corrections, you understand, you put more V's here, more integrals here. So that is the form of the first wrapping correction.
one bridge, they were not acting on the two other bridges. One of them was trivial because there is a
Because of this conformal frame. I could put them at -1, 1, then they would act on both.
But this hexagon seems to be symmetric against all the bridges, which is a bit confusing in this conformal frame.
That's right, because this statement that the derivatives just act here, it's a bit schematic in the sense that I can always do a conformal transformation. Now the derivatives just act here. It's not a gauge invariant statement where the derivatives act. It's an artifact of the way you did the computation.
So in some sense, the hexagon is somehow more fundamental than this picture of how you think about the bridge.
Yeah, that's right. This hexagon now is final, and when you go beyond tree level, beyond this picture at one loop, this is super complicated because you need to correct this state. You need to insert loops here, so it's not just about weak contracting states. It's much more. It's not just scalar products of spin chains. It's much more. But this formula works. So this formula is the way of doing it correctly. So what time is it? I think I'm probably out of time. I wanted to say a few things about another formulation, but I think I'm probably out of time. 3:51. So I'm already 4 minutes over time. So let me just say something that I think in n equals 4, what we are seeing that it's very natural to cut the states with these hexagons. It's very natural to take pair of pens, to take this sphere with 3 punctures, and cut it in this funny way that cuts through the physical operator. It's not something that we are normally used to. Normally we have operators and we cut around. We don't cut through the physical operators. We don't start putting cuts that go exactly through the vertex operators. It's a bit, but it seems to be the only way we know, and the best way we know so far, of computing correlation functions in this theory that is more complicated than flat space. So I would like to think that this hexagon is really a fundamental object, and that if I have that perhaps there could exist a string field theory or something where it would not be the 3-point pair of pens the fundamental object, but rather this hexagon. And I would hope that if I would use this hexagon, things would simplify, and instead of using infinitely many vertices, I would only have this hexagon. And of course, the key thing would be understanding what she was asking. What exactly are these Hilbert spaces, and how do I make it more rigorous, and so on. And I think if we could, it would be awesome if we could describe a string theory that would be based on this hexagon and not based on the pair of pens. Because it seems like here, this is more fundamental than this. Yeah, okay, I'll stop here. It's okay.
I was wondering if you could say something when you have these sprinkles on more than one side.
When I have?
The derivative sprinkled on more than one side. Let's say two sets
Right.
of operators.
For example, if 2 have derivatives, so let's make this one non-BPS. Let's put also derivatives here. Then what would change is that now I would have particles here and particles here. And so now I would end up in that case with a summation over ways of splitting alpha and alpha bar, a summation over splitting the particles in the bottom, let me call them V's. And then there will be some weight factor of bridge length L for particles that tell that what's the weight for the particles alpha to go to the back. There will be some weight factor for the particles beta to go to the back. So this, and now that alpha went to the back and beta went to the back, the hexagon now knows about alpha and beta, not just alpha, times an hexagon that will know about alpha bar and beta bar. And in pictures, I would draw this picture. I would say that I have an hexagon here times an hexagon here. And in this hexagon, I get some alpha and some beta. And in this guy, I got some beta and some alpha bar. I wrote here an example with spin 6 for both operators. And that would be the leading form up to wrapping. And then if I start having wrapping, I start adding an extra particle, for example, an extra W and minus W, and then I would put an extra integral dW, and I would add an extra W here and the W here, and so on with more and more mirror particles.
So about the wrapping interaction, when you, I would assume you also need to correct for the UJs by the mirror particles, like in the beta equation themselves.
That's right. So this formula here gets more and more and more corrected, but you are right that the notion of this use gets corrected, and you need to take into account the wrapping corrections in the interaction of the use, yes.
And do you have to work to consider the beta strings, not just the elementary SL2 magnons?
I only need to consider the elementary ones, because these beta strings that you are referring to are the virtual ones that we sum over, but the physical ones, they are not strings, they are just the usual real magnons. When you start summing many particles, that you start getting wrapping not only on one edge, but on both edges, that's when you start getting a virtual particle that really goes around the full thing, because you put a particle that really goes around the full thing. So to get wrapping corrections that start mixing with the wrapping corrections of the spectrum, you need at least two virtual particles, one on each side. Then what you see is that this hexagon has a problem, that when you put particles on both sides, you will start getting a pole when these guys coincide, and you need to regulate this hexagon business. And that's what Basso, Benjamin, and Alessandro, and so on have been working on, and understanding that this divergence is physical. It's nothing but a renormalization of this operator and how it relates to the fact that this operator needs to be renormalized by the effect of these virtual particles, and they managed to take that into account.
Do you think this factorization is naively some manifestation of double copy?
It has the flavor in the sense that we are breaking a closed string into two open strings. Yeah. It has that flavor, but it's not that direct, I think, because these are not on-shell open strings, right? So this double copy and KLT, right? It's a bit more than what we are doing, because it's really saying a closed string scattering is a linear combination of on-shell open string scatterings, right? Although deformed. And here, no, here it's a more brutal cutting. I have excitations, and for example, they have total zero momentum, which is like the analog of level matching in bosonic string. And now I cut, and I put some in the front, some in the back, so no level matching, and so on. So the front and the back, they are not independently two on-shell open string processes. They are some off-shell version of it.
If you consider large dimension operators,
Mm-hmm.
in the full loop calculations, different diagrams will scale different with the dimension. And take a limit where the dimension goes to infinity,
Mm-hmm.
some diagrams could be set to 0, and you will have a set of surviving diagrams.
Yes.
Do you see in the hexagon picture, can you see that kind of simplification if you take large dimension operators?
Yes, you can. What happens when you take operators, for example, these operators, some of them are big and dual to big classical strings in ADS 3. Well, strictly speaking, that's when you go to strong coupling. But even at weak coupling, if the operator is very big, you can think of them as a classical motion in some Landau-Lifshitz model, where I have some spins that are moving slowly as a coherent state. So it's some big classical thing. That regime, where this takes some kind of classical limit of some long wavelengths that are changing slowly, that's the regime where these U's are very big. Because these U's are very big, these functions here, big plus I over big, is almost 1. And so what happens is that these terms are very close to 1, and in fact this full sum exponentiates. And then in the exponent, you recognize the action of that Landau-Lifshitz model. So that's how that emerges. And in particular, if you do this computation, taking these hexagons and going to strong coupling, you recover the area of minimal surfaces inside ADS 3 times S1.
What happens if you go beyond the SO2 sector in this construction?
You have to generalize now this hexagon. If I do operators with any polarization, this hexagon is really a tensor. It's not just a number. And I need to put indices here.
But the results are then.
Yeah. So it turns out that when you go to the full sector, if you might remember that people found the S matrix by recognizing that the S matrix was a tensor with SU2/2 square symmetry. The hexagon is a tensor with SU2/2 only. It's one copy. But one copy is usually enough. And indeed, it's enough to fix the full hexagon tensor structure.
So this smells, at least from my intuition, it only works if the theory is integrable. Do you think this generalizes to string theories which are not integrable?
I think so. I think what's special about integrability is that the label of the states is very nice. Is that there is a notion of summing over states is just one integral, two integrals, three integrals, and so on. This notion that resolving identity is trivial. But the idea that if you cut, there is some state there is always true. So I think you can always cut an hexagon in two. That no one can stop you. But the resolution of identity, the fact that it separates into selection sectors where it's vacuum, one particle, two particles, three particles, that is special to the theory being integrable.
So if you slightly deform
If you slightly deform, I don't know. I don't know. I would still label the states. I would still say I have state 1, 2, 3, 4, but they don't have this simple characterization as one particle, two particle, three particle.
So I have another silly question. So there's a special state where you have BPS in your spin set, right?
That's right. That corresponds to putting no use. Make all the use the empty set. So BPS means this goes to the empty set.
What about some 4-point functions being protected in some special domains?
Right. So 4-point functions that are protected, it's very interesting. So the way it works, it's so when you have 4-point functions, the way you consider these 4-point functions is by cutting into hexagons again, but you don't cut it into two pair of pens. It's not like in the OPE where you cut one and you cut another. No, the way you cut is triangulating really the surface. It's like this. So it's really what I wanted to say. It's very different from the usual three-point function, right? We are really cutting through the physical operators. And I think it would be super awesome if we could understand this computation from a worldsheet point of view. How do I define some hexagon and cut it like this? Don't cut like this, but cut it in this way. By putting some appropriate twist field operators and I don't know, I think even in flat space, trying to understand how do I reproduce Virasoro-Shapiro in some fun computation where I split the worldsheet computation into triangles.
If I consider just the extremal three-brane solution asymptotic flat, is there no integrability? Is that there's no chance of integrability?
You mean what people want to put to add this TT bar like deformation?
Just restoring the asymptotic flat, like not taking the common limits. Just restoring the asymptotic flat, just having the solution, interpolating the ADS5 and ADS5 and flat space.
That's right. I think we believe that's not integrable. I think Leonardo studied a bit that with João Caetano, but it's not something I know well. It's 4:04.
Sure. Okay, so 5 minutes.
this you can put on the pocket
Okay, you don't
or
want to
on the
use
pants, no
slides.
problem.
Mm-hmm.
You can use slides also if you want.
Just press.
Prefer to make it flat, but first, but no, she insists you can use slides.
Okay, so I want to talk about some kind of technical aspect of computations in ADS CFT, in particular computations which would arise in the context of pure spinor formalism. And I think the main topic here is to take, so we use pure spinor formalism where physical states corresponds to heuristic homology, and more precisely, physical states corresponds to heuristic homology at Gauss number 2. So we consider type 2B on ADS 5 cross S5. That's about the only example which consider usual ADS CFT context. So we know how to describe small deformations of this background. They correspond to vertex operators of Gauss number 2. So there is some BRST complex, and homology at Gauss number 2 describe deformations of this space. And they also correspond to operators in the Young-Mills side. So if we consider the correlation functions, for example, 3-point correlation function, this would correspond to some kind of integral over ADS of the product of 3 corresponding vertex operators. Although there is no precise prescription, but there must be something like this. But so each of them has Gauss number 2. And they are annihilated by the supergravity BRST operator. But they're non-trivial in cohomology, so they're not Q of anything. But the product of them, so the baristic homology is non-trivial in Gauss number 1, 2, and 3, it turns out. Sorry, I don't know, maybe there is something at Gauss number 4 also, but there are finitely many. So there is finitely many at Gauss number 1, Gauss number 2, and Gauss number 3 are more or less equivalent, modular 0 mods. But the product, of course, should have has Gauss number 6, so it's BRST trivial. So exists some operator W such that the product is QW. But so naively, the correlation function should be 0, but somehow the subtlety should be that W does not have good behavior at infinity in ADS. ADS is non-compact space, so W should be not admissible type. And therefore, the integral is actually, integral of Q of W is not 0. I don't know how it works in details because I don't know precise prescription about how you integrate over ADS. But in general, what happens here is that W is not admissible because it has some bad behavior near the boundary of ADS. So how do we measure this bad behavior? Apparently, the product of V1, V2, V3 was admissible, but W was not admissible.
Sorry, why do you say you don't know the prescription for integration? Isn't this just the sphere 3-point amplitude in the usual prescription?
Well, in RNS, I don't know how to describe.
No, I don't mean RNS. I just mean like I thought you were talking about in just the pure spin-Rorschach theory. The
Yes.
usual 3-point amplitude is what goes wrong.
3-point amplitude. Yeah, you can just integrate. I guess the question is how you integrate over pure spinors. Strictly speaking, they are linear in pure spinors. So there are two pure spinor variables which transform in, which live in the spin bundle over ADS. We will call them lambda left and lambda right. So this vertex operator is something like lambda left alpha, lambda right alpha hat, V alpha alpha hat function of G, where G describes point in ADS, super ADS. So I would integrate them over d lambda and dg. Integral over dg is non-compact, and it should but the integral should converge in principle. With integral over lambda, I'm not sure what to do.
Sorry, first, just to be sure, when you say ghost number, you mean the number of lambdas?
Yes. Yes.
But you say there's no actual prescription for the measure?
Yes, there's none that seems to give the right answer. So naively, you want to integrate over all 32 thetas? That's too many. In the class space, you integrate over 10, so.
I don't think I know the prescription. So yeah, sorry, this is very hand-waving talk. But the idea is that somehow the behavior near infinity, so there is something that makes integrals of the product of 3 V's well-defined, but W at the same time is not admissible. Intuitively, the only way this would happen is that the behavior at infinity is dictated by the representation in which the objects transform under the action of isometries of ADS, I think. So it must be true that W does not transform in the same representation as the product of V1, V2, and V3. So if each of these vertex operators transform in some representation of superconformal algebra, which is a superalgebra of superisometries of ADS. So VI transformed into some representation of superalgebra, which I denote G. G is PSU224. Then the product transforms in the tensor product of two representations. But apparently, it is impossible to find equation QW equals VVV. It is impossible to find W transforming in the same representation as it's not true that W transforms in the tensor product of H1, H2, H3. When we solve equation QW equals VVV, the non-trivial extensions of representation appear. So there is some representation X. There is non-trivial extension. So the kernel, here is some subspace of operators of Gauss number 5. And Q gives me the tensor product of three representations. The object which transforms in the tensor product of two representations. So the solution for equation QW equals VVV is defined only up to some operator which is annihilated by Q. So there is some operator which is annihilated by Q and which has Gauss number 5. So there is some subspace in the space of Gauss number 5 operators and subspace into it of the Gauss number 5 operators which are annihilated by Q. And it must be true that this solution for Y5, you cannot gauge fix it without breaking superconformal symmetry, without breaking superisometries. So this extension is non-trivial. Now the cohomology at Gauss number 5. So technically you can say that you just solve W, just solve somehow for W, and then you act on the solution by you solve on W as a product, as a function of product of VVV, and you act by element of the conformal algebra and see what is the difference if you act on this V's. So you should act on each one. And this will be some expression which depends on Xi. So let me call it psi of Xi. It's a function of element of Lie algebra, and Xi is G, and it belongs to, we know that it belongs to the kernel of Q. Because the cohomology class transforms, because Q of it transforms into representation of VVV. Q of it is just VVV, so the difference between these two should be in the kernel of Q. But cohomology of Q at the Gauss number 5 is trivial. Therefore, exists some x4 such that x5 is Q of x4. And x4 is, again, it does not transform in the same representation of x5 as x5. There is some, so I should call it y, to be consistent, I would call it y4. There is some operator such that Q of y4 gives x4, but it is defined only up to something that is annihilated by right? Annihilated by Q. But there is no Biresty cohomology at Gauss number 5. So eventually, x4 is also Q of something.
X5 is that psi dependence object? X5 depend on psi?
Yes, x5 depend on psi. Then x4 would depend on psi and eta. And x3 would depend on psi1, psi2, psi3. It will be annihilated by Q, and there is a cohomology at Gauss number 3. Cohomology of Gauss number 3 is the same as cohomology at Gauss number 2. B0 minus, in bosonic string, B0 minus B0 bar connects the two spaces. In pure spinor, there is no such thing as B0 minus B0 bar, at least I don't know how to deal with it. But however, I know by direct computation of cohomology that cohomology at Gauss number 3 is the same. So these are basically physical states. So what I got is this x3, and then I take x3, it's annihilated by q, but I take it modulo q of something, and it gives me the some physical state. So I have element of the third cohomology group of Lie algebra G and PSU224 with coefficients in maps from tensor product of three physical states to, again, the physical states. And so my claim is that supersymmetry allows often to guess or to derive what this cohomology class is, and in some sense the correlation function should be related to this cohomology class. But I don't know precise formula how it is related. So I give one example of what happens.
So you say there's a physical state with three adjoint, so it's like three adjoint representations. I'm just looking at X3, right? So there's a physical state which is constructed out of three, whatever you call them, three things in the adjoint representation. Is that what you're saying? I'm just looking at X3.
Yeah, so this was the claim is that I can start with the product of three vertex operators, and out of product of three vertex operators, I somehow can cook for you. So I can introduce to describe Lie algebra cohomology, I introduce spectator ghosts, which are, and then, so I will have something like CA, CB, CB, CC times psi ABC, which is a ghost number 2 operator. So out of product of three ghost numbers, two operators, which has ghost number 6, the product, I construct ghost number 3 vertex operators by this procedure, which is more or less the same as ghost number 2 vertex operators. And sometimes you can try to bootstrap this or guess what the result is. And moreover, the correlation function should be expressed, but I don't know precise relation. But this psi ABC in some sense should be correlation function. There is a precedent in bosonic string theory. There was a paper of Bergman and Zwiebach where they studied non-decoupling of dilaton zero mode. And it's very similar mechanism. It should be similar mechanism. But at the moment it is a hand waving. So let me give an example of how non-trivial extensions appear. So this cohomology group is also called X3 of G or UG. H1, H2, H3, H. And elements of, so generally speaking, elements of X3 of AB would be equivalence classes of exact sequences. Of 5 elements modulo some equivalence relation. So we can guess the corresponding exact sequence. So we give more or less the only example where I know how it works explicitly. There is for each conserved current, so for each element of G, corresponds Gauss number 1 vertex operators, which I call lambda of psi. It corresponds to, because global symmetries corresponds to cohomology of Gauss number 1. So this has Gauss number 1.
So if you get an explicit formula for psi, you won't need the Pierce-Pinero measure. Is that what you're saying?
Maybe. I don't have precise statement, but the statement is, somehow what Bergman and Zwieback did in bosonic string could be repeated here. I tried to start doing it, but I don't have yet at the moment the result. So in ADS notations, this lambda of psi is something like supertrace. Well, we don't need to know the details. The ADS is described by group element of the group PSU. And thank you, Nathan. So it's just pairing. It's just psi, scalar product of psi with this element which happens to be annihilated by by Q. So this is annihilated by Q. Nathan discovered this in 2007, this expression. So it's annihilated by Q, and so this is Gauss number 1 operator, which depends parametrically on psi. Now I want to multiply it by another, by a Gauss number 2 operator, which is just supertrace lambda left, lambda right. So lambda are pure spinor variables. Supertrace lambda left, lambda right is a Gauss number 2 operator, physical. It corresponds to changing the radius of ADS. It's usually called dilaton zero mode. This happens to be BRST exact. Generally speaking, if you have a Gauss number 1 operator times Gauss number 2, then the obstacle to this being BRST exact is the action of psi on this operator, the action of the symmetry on this operator. In this case, this operator is a scalar. It's a constant on ADS. Symmetry acts on it 0, so this is BRST exact. It's Q of some W, where W depends on psi, of course, linearly. But it turns out that in order to find W explicitly, I have explicit formula for it, which is rather complicated. But interesting feature of this formula is that it requires representing psi as a commutator. Psi1 commutator psi2.
Sorry, just to understand the interpretation. You're calling dilaton zero mode, but I mean that I would have thought that the change of that doesn't correspond to change of radius. I thought the change of radius would be off shell, no? I mean
Change of radius of ADS. No, it's G square n.
That would be the phi form. You mean to deform the phi form flux?
This descends, the corresponding integrated vertex is, yes, no, it's phi form flux is integer, but there is also the radius over alpha prime.
Oh, okay.
So this, on the descent, the corresponding integrated operator is just Lagrangian of string Wolfsheets theory. So you just change coefficient in front of the Lagrangian. You change alpha prime. So if you split, in any way, if you split for me psi as a commutator of psi1 and psi2, then I can write W for you. But the problem is that in supersymmetric case, this cannot be done covariantly. If it were bosonic algebra, for example, SU4, I could have said that could have written something like FAB. So if psi equals psi A TA, where TA are generators of the algebra, then I would say that it is equal to 1 over quadratic Casimir of psi A F ABC, TB, TC, and then I substitute this into this formula. So here I need Xi1, Xi2, Xi1 wedge Xi2. But, and resolve. But this doesn't work in supersymmetric case because C is 0. So I can always represent Xi by commutator of two elements. There are many ways of doing it. The problem is that I cannot possibly do it in a covariant way, which would be consistent with the action of supersymmetry, because there is a non-trivial extension of Xi transforms into adjoint of symmetry algebra, and there is a non-trivial extension by operators which by wedge product of two sorry, I just write G instead of adjoint G for brevity. So there is a non-trivial extension, and this non-trivial extension, this is not split, so you cannot do this. It's not non-split, so it represents non-trivial x1 of G with G 0, and when I project to BRST cohomology, in this case I have x1 of G. It generates x1 of G with G 0 internal. 0 means 0 internal commutator. Modulo G, modulo diagonal, modulo this embedding. And this is the space in which beta deformation of ADS transforms. So on Voltsheet, in Voltsheet theory, beta deformation corresponds to adding to the Voltsheet action with some coefficient the wedge product of two currents. And it is some deformation of ADS CFT, which was investigated by Ley and Strassler. Appearance of it in this context is, I don't know interpretation. The formula for W was useful for us in some computation of, but I don't know the physical meaning of why multiplying current with dilaton 0 mode gives me beta deformation after this procedure. More precisely, beta deformation, in this case I have x1, so I have CA times CA, where CA is a vertex for beta deformation. Beta deformation. So for somehow this procedure generates out of the simplest deformation of ADS cross S5 the next more complicated deformation, which is beta deformation. Another, so now this is again the
Infinitesimal beta deformation?
yes, infinitesimal. I'm talking about linearized. So vertex operators of Gauss number 2 corresponds to linearized deformation of ADS. Another example, I can take several.
What can I do with this result? If it's linearized, is this useful for something?
Immediately, this explicit expression for W was useful in some way when you construct next orders. We used it in our paper with late Professor Revelis, so Bedoya, Bevilacqua, Revelis, and me. And it was useful for something, but at that time we didn't realize that it is actually, that it has this cosmological interpretation, that resolution. And there are more such examples. So I think these examples, I don't know for what they are explicitly useful. In particular, I don't know how such resolutions are related to correlation functions. I just don't have precise statement. But in any case, I believe that they will be useful intermediate stepping stones in ADS computations. with pure spinors. For example, I can consider several lambda of, so let's see, lambda A, I denote lambda of the basic generator of the algebra. Better put index down. Then I can consider with some B, A1, A2, AN, I can consider lambda A1, lambda AN. When n equals 2, by the way, this is beta deformation vertex in unintegrated form. But for n greater than 3, it will be resolvable. So I can play this zigzag game, which I outlined, and it will give me some element of x this is the wedge product of this representation, which is basically antisymmetric tensors of n. It's almost the same as G wedge G n times, wedge product of n copies of a joint representation. So I have, but you have to impose also some tracelessness condition and divide by something. Adjoint G power n with coefficient is beta deformation, and x would be n minus 2. So this corresponds to long exact sequence, which is the Kashul, something like Kashul complex of G. Very schematically, it's G wedge G modulo something. I cannot write it explicitly, I don't have time, but there is some product where you have wedge, sorry, here comes, so x goes the other way around, from right to left. So you start here with beta deformation. Beta deformation is G wedge G 0 modulo G. And then your wedge product is with unit matrix and antisymmetrize. So you have G wedge G wedge G. Then it ends up with this lambda and G. So there is some long sequence which generate acts which conjecturally corresponds to the resolution of lambda of wedge product of n lambdas. I don't know how to do this computation explicitly. Another example is taking trace, for example, dilaton vertex, trace lambda left, lambda right to the power n, and this is Q of something. So I have some conjecture about what such expressions could generate in terms of X groups. Unfortunately, I don't have time to explain it. Although I have to mention that my former student, Denis Zavaleta, had some progress in actually explicitly. Recently, he told me that he resolved this trace of lambda left, lambda right to the power 17 plus at least 17. He knows explicit expression for this, but only first step. Then you have to take. Then you have to act by symmetry again and take Q inverse again and again and again and again, and you descend all the way until ghost number 3 or ghost number 2. I think most likely it will end up on ghost number 2. So the conjecture in general is that there are finite dimensional representations which participate in deformations which transforms in finite dimensional representations. They correspond to tensors with fundamental indices of PSU, lower and upper, and number of lower indices should be equal to number of down indices, and they correspond to supersymmetric Young tableaus. So you cannot, for superalgebra, you cannot express upper indices in terms of lower indices like it was for SLN, because there is no determinant. But so you have to separately specify representation of upper indices and lower indices. So this, for example, corresponds to trace z to the power, so it should be the same number, z to the power 5, where z is the complex combination of two scalars of n equals 4 Superyoung-Mills. So if you take integral d for x and this and start acting on it by superconformal algebra, you get this representation, finite dimensional. And so I call it H5 because it corresponds to Z5. And then it turns out that there are exact sequences like Hn something Hn minus 1. So I have a conjecture that these representations are irreducible. I think this is a gap in ADS-CFT correspondence because we don't know, strictly speaking, what are these representations. So unlike usual bosonic algebras, the representation theory of finite dimensional representations of superalgebras are not semi-simple. They do not split into direct sums of irreducible representations. So there are non-trivial Jordan cells, which are described by these cohomology groups. So my conjecture is that operators like this transform in irreducible representations. It's conjecture just the simplest guess. Then if they are irreducible representations, then there are such sequences. Basically, you have to take traces. And if you take traces twice, then you get 0 because of symmetrization and anti-symmetrization. So upper indices and lower indices are opposite in terms of symmetrization and anti-symmetrization. So if you take trace twice, you get 0. So that's why 2 steps. So there is basic x2 of hn plus 1. Surprisingly, if I understand the structure of these representations correctly, then they have scalar products. So there is also a dual there are some dual diagrams, hn plus 1 hn. And by considering concatenations of these diagrams, there is a thing called Yoneda product. If you take 2 such diagrams, you can fuse them, and there is product. The product acts from xm to xn to xm plus n. So the conjecture is resolution of such invariant polynomials would give me the chains of products of these sequences. This is very far from proof, and it's a wild guess. And also, I must say that they easily can leak into infinite dimensional representations. So I don't know how to do computations here. In spite of its elegance, the pure spinor formalism does not seem to be particularly suitable for, I don't know how to do computations. I mean, Dennis, for example, explained to me how to do computations with this object. In Natal, people do some computations with them. And they know how to really write BRST complex and do it partially on computer. It's a combination of symbolic and numerical techniques. So maybe it would be possible to these are natural intermediate questions which can be asked in this type of computations. And there is also a relation between these cohomological methods with glyphographic renorm group, which is very subtle, but I cannot talk about it today, obviously, because I think I ran out of time, right? Sorry about that. Run out of time? Well, yeah, there are I mean, one open question which I think exists in this idea CFT is to understand the structure of finite dimensional representations. This type of Young diagrams also appeared in Y system. I don't know if they're related or not. But the statement is that they are
Can I ask something? So is it known to just take n to be 3? Is that supposed to be non-zero? Do you know?
I think it's exact. I think 3 is exact. About 2, I'm not sure. I have a paper about it, but I forgot now. I think at ghost number 4, there are some non-trivial combinations.
That vanishes.
For 3, it vanishes, yeah. So you can ask, it will give me x, some element of x.
So you think you can write that as cube something, whereas something is manifestly PSU2 invariant?
Of course not, because if it were manifestly PSU2 to 4 invariant, then it would be, then Q would act 0 on it, right? Q acts 0 on these expressions. So all the PSU2 to 4 invariant things can be written as invariant polynomials of lambdas. And Q BRST acts as 0 on lambda. So the resolution will necessarily introduce some other representation, non-trivial extension. It will be extension of constant trivial representation.
So I'm just trying to ask, is the 3-point function supposed to vanish or not? If you have 3 radius modulators, anybody know?
You mean just the Lagrangian density?
Mm-hmm. Well, it's embarrassing, but I don't know the answer to this question.
Vanish because it's an exact marginal deformation.
But I'm not sure if it's even well defined, because if you try to
If it doesn't vanish, it would obstruct the marginality of deforming the Young's coupling.
Okay.
what?
It has to. The 3-point function has to vanish because if not, it'll be obstruction to exact marginality.
Mm-hmm.
More generally, the 3-point function of Lagrangian with the 2 BPS will vanish, right?
Yeah, that's right.
How do you know that there are no obstructions?
If you integrate the Lagrangian, that's like derivative effective coupling of that quantity, and that quantity is coupling independent.
Okay, so that's a clue. So
I'm not sure that for finite dimensional operators this is always well defined, because you have collision of integration points.
he's just saying that if you take 3 half BPS operators, and if one of them is Lagrangian, then you can't get an
By the way, just to understand what you're computing here, I thought usually we want to take the 3 operator to be at different spatial position, not like smeared out in space, right? So, but here you are considering like the actual 0 mode.
Well, it's the reason, to be honest, the main reason I'm doing it is I just wanted to play with finite dimensional representations. The story, when you insert them at a point, then you get something like infinite dimensional representation, right? So the story is the same. I have not studied properly. So for finite dimensional representation, I have a bunch of conjectures or statements about how this X groups looks like, at least some. For infinite, I haven't studied properly. But yeah, you're right. Since I started by saying that my motivation is to study correlation function, and I'm not sure if these correlation functions are defined even for finite dimensional objects, because there are collisions and divergences. But so I should study it instead for infinite dimensional. But surprisingly, I must say that if my conjecture about finite dimensional representations is true, then it seems that it turns out that they have scalar product. They are equipped with scalar product, which are of course non-positive, but it's invariant. And so this is one of the questions. What could possibly the scalar product be? It's like a two-point correlation function, integral trace Zm, integral trace Zn. Well, this one is 0, but you act by a bunch of supersymmetries. Is this expression well defined? Is it possible that there is something like the Molodchikov metric on these deformations? So I want to consider deformations of Young-Mills with coupling constants space-time dependent. So add arbitrary smeared operators. And then I want to ask if there is something like invariant metric on them, which is given by integrals, by correlation functions like this. Naively, they are infinite, of course, because of the collisions. But maybe there is a PSU invariant, maybe there is superconformal invariant regularization of them. And then there are some invariant metric. Not metric, because it's not positive definite. Mm-hmm.
Okay, let's thank Andrei.